So today we're going to continue with the rates topic. We're going to move away from graphs just because it's too difficult to do that remotely. I'm assuming a lot of you won't have graph paper at home. And we're going to move on to the last part of the rates topic, which is collision theory. I'm going to jot down a few notes to explain what I mean by collision theory. You are more than welcome to take them down in your science book if you want. You don't have to because they're already in your booklets, but if you like taking down notes, then by all means take them down as well. So we are still looking at rates of reactions. So I'm just going to jot down a reaction, an example reaction. So I'm going to react hydrogen and oxygen. Hydrogen's diatomic, so I write it as H2. Oxygen's diatomic, I write it as O2. And when I react H2 and O2, I'm going to get H2O. Is it balanced? 2 hydrogens and 2 hydrogens, so that's all okay. 2 oxygens, only 1 oxygen, so I need to balance it. I can't use a small number when I'm balancing. I have to use a big number, so I'm going to have to put a big 2 here. Now I've got 2 oxygens and 2 oxygens, so that's okay. But now I've got 4 hydrogens. I need 4 over here, so I'm going to put a 2 there. Okay, so this is just my example reaction, which I'm going to use to explain collision theory. So in order for this reaction to work, in order for your hydrogen to react with oxygen and make water, your hydrogen molecule and your oxygen molecule need to actually collide with each other. Okay, so they need to physically come in contact with each other. So for the reaction to take place, the reactants, so I'm just using the word reactants to describe hydrogen and oxygen, but you can use this word for anything that's on the left-hand side of an equation. The reactants must collide. In this case, the reactants are hydrogen and oxygen, H2 and O2. And not only must they collide, but they also have to collide with energy. Collide with the required amount of energy. What I mean by that is, let's just say, see my hands, let's just say my left hand is hydrogen and my right hand is oxygen, okay? I need them to actually collide for the reaction to take place. But if they don't collide with much energy, what's going to happen is they'll collide and then they'll just bounce off each other and you won't get a chemical reaction. I need them to collide with the required amount of energy, and this amount of energy, as we'll see in a later topic, is going to vary from reaction to reaction, but I need them to collide with a significant amount of energy so that when they collide, they actually form water. They're forming my product, they're forming water. I don't want them to collide and then just bounce off each other. So they need to actually physically collide, come in contact with each other, and they need to collide with energy. If that happens, then your reaction is going to take place. Your hydrogen is going to react with your oxygen and you're going to form water. And this is true for any reaction. So if I took a different reaction, if I took carbon, I'm going to react carbon with oxygen and I'm going to form carbon dioxide. Oxygen, again, it's diatomic, so I'm writing it as it's O2. Carbon and oxygen gives me CO2. This one's already balanced. For this reaction to take place, my carbon, which can be my left hand, and my oxygen can be my right hand. They have to collide, and they have to collide with a significant amount of energy. We've been looking at rates of the reaction, so I'll remind you that when we're looking at the rate of a reaction, we are looking at the speed of a reaction. We're looking at how quickly that reaction takes place. And what we're going to do is we're going to use this collision theory to predict or to come up with ways that we can increase the speed of a reaction. Okay, so if we know that the reactants have to collide, and if we know that they have to collide with energy, there's lots of different things that you can do once you know that to increase the speed of the reaction. You just need those particles to be colliding and colliding with energy. And there are 5 different things that you can do that's going to cause them to collide with each other more frequently and with more energy, which is going to give you a faster rate of reaction. Today we're going to look at 3 of them. The first one we're going to look at is surface area. Surface area, okay? So if we look at surface area, okay, so for example, I'm going to draw I'm just going to draw a big squiggly shape, right? And this is going to be my carbon. Just say this is a piece of carbon. Okay, carbon's typically just coal, by the way. This is a piece of carbon, all right? And then I'm reacting with oxygen. And the oxygen molecules lots of them can collide with my piece of carbon. But you can see that they can only collide with the carbon with the surface of the carbon on the outsides, because that's the part of the carbon that's actually exposed to them. And you can have lots of collisions around the outside between oxygen and this piece of carbon. But if you took this same piece of carbon and you broke it up into lots and lots of different pieces, so all of these individual dots are now representing my carbon. I should use a different color. Okay, actually, I'm going to color them in. These are all my pieces of carbon. So I've taken that same big lump of carbon and I've just broken it down into lots and lots of different pieces. So imagine, oh, this is my big piece of carbon. I've now broken it down into lots and lots of individual pieces. And by doing that, there is way more surface area. So for example, that tiny little piece of carbon can be attacked, or something can collide with it on all three sides. I can get way more oxygen molecules around carbon when I've got carbon in tiny pieces than I could get around carbon when I just had a big lump. So there is way, way, way more surface area when I've taken my piece of carbon and broken it up into tiny pieces than when I had my piece of carbon in a big lump. If you have got more surface area, you have got more collisions. If you've got more collisions, you're going to have a faster rate of reaction. Okay, the quicker those particles are colliding, the faster your reaction is going to be. So underneath here, surface area, I'm going to write if you increase the surface area, you are increasing the frequency. So how often are happening? The frequency of the collisions. And if you're increasing the frequency of collisions, you are increasing the rate. Okay? Increase surface area, increase the frequency of the collisions, you are therefore going to increase the rate. Okay? The more collisions that are taking place, the faster the reaction is going to go. If you break it into tiny pieces, there's more surface area, you're going to get more oxygen molecules around that same piece of carbon. More collisions, more product, faster rate. The other thing that you can do, okay, and this one's probably a little bit more obvious, is you can just increase the concentration. So for example, if we were doing a practical and we're all back in N32 and you're all wandering around the room, okay, typically you don't crash into each other, you don't collide with each other when there's only 30 of you in the room. But if I were to take the other 4 Year 9 classes and throw you all in N32 together and ask you to wander around the room, with that many people in the same room, you are likely to collide with each other. You're likely to bang into each other. And it's exactly the same for particles, okay? The more particles you put into a beaker, the more likely they are to collide with each other. And we call this changing the concentration. So if you increase the concentration, so if you've got increase the concentration of particles, so if you put more particles in there, increase the concentration of particles, you are going to increase the frequency of collisions, and you're going to increase the rate. Okay, so for example, if I had a beaker here, I'm going to do 2 different colored dots. This is going to be reactant 1. That's a really awful pen. That's going to be reactant 1, and this is going to be reactant 2. Okay, they're going to collide with each other. You're going to get a reaction. But if I, in that same beaker, if I threw in way more dots, if there were way, way, way more particles in there, then they are going to collide more frequently. More of them, they're going to collide more frequently. If they're colliding more frequently, the rate of the reaction is going to be faster. The other thing that we're going to change is pressure. So this is similar. This links to concentration. So I said if you were all in N32 and you were all wandering around, that you probably wouldn't collide into each other when there's only 30 of you in the room. But if I took you and I put you in, that little prep room that's next to N32, it's really, really small. I don't know if you've ever been in there. Basically, it's a really, really small room. And if I took all of you and put you in a really small room, then you are very likely to collide with each other. And it's the same with particles. Okay, so if I had a big space and I had my particles. Okay, so this, sorry, I should mention, this only applies when you're reacting gases together. So in a gas, the particles will take up as much space as they possibly can, and they'll be as far away from each other as they possibly can. So if I had, pretend this is my hydrogen-oxygen reaction, so I'm going to have 3 hydrogen molecules in there, and I'm going to have 3 oxygen molecules in there, and they're going to spread out and be as far away from each other as they possibly can. If I increase the pressure, and by increasing the pressure, you are reducing the space, those particles are suddenly a lot closer together. And if they're closer together, because remember they are moving all the time, if they're closer together, they are far more likely to collide with each other. Okay, so this is only true for gases. I'm sorry about that here. Pressure, only true for gases. Okay, but this here would be a low pressure. By low pressure, I mean they've got lots of space. And then this picture here would represent high pressure. So if it's low pressure, you have got more space. High pressure, you've got less space. And if there's less space, those particles are going to collide more frequently. If they're colliding more frequently, you are going to get a greater rate of reaction. So all of the factors we've looked at so far have referred to this point, getting the reactants to collide more frequently. We haven't talked about this at all, about getting them to collide with more energy. That we're going to look at in the next lesson. For now, I just want you to focus on these 3: surface area, concentration, and pressure. All 3 of them, if you increase the surface area, if you increase the concentration, if you increase the pressure, they will result in more frequent collisions. More frequent collisions means a faster rate of reaction.